Now that you've had a chance to learn about what the polar form or modulus argument form of a complex number is, let's look at how nice it makes multiplication and division, and then in the next video we'll look at how nice it makes raising complex numbers to an exponent. So if we have z1 and z2, and in its polar form z1 is r1 cis theta 1 and z2 is r2 cis theta 2, then it should follow that z1 times z2 is r1 cosine theta plus I sine theta 1, of course, times r2 cosine theta 2 plus I sine theta 2. That is a mouthful and it looks horrible, but it's actually a really nice thing. So let's go ahead and digest what we have here and try to do some simplifying and make this a little bit more usable. So this, since it's all multiplication, we can write as r1 r2 times, well, these are two binomials that we're multiplying. So let's go ahead and FOIL. Cosine theta 1 cosine theta 2 plus I times cosine theta 1 sine theta 2 plus I sine theta 1 cosine theta 2 plus I squared sine theta 1 sine theta 2. And how you might be saying, well, how does that possibly make this better? Because it's even bigger and nastier and ickier than it was before. And you're right, it is right now, but bear with me, stick with me. This is going to get nice. So inside here, we have that and that don't have i's. And you're saying, but wait a minute, that last one has I squared. But aha, I squared is the same thing as negative 1. So what we really are looking at is cosine theta 1 cosine theta 2 minus sine theta 1 sine theta 2. And I'm going to group those together because they don't have I. And then the other two terms have i's. They can see. Ha, I'm funny. So cosine theta 1 sine theta 2 plus sine theta 1 cosine theta 2. And if you paid attention in trigonometry study, you will notice that this is simply the addition identity for cosine. So what we have is r1 r2 times cosine theta 1 plus theta 2 plus I, and this other one, that thing, is the compound identity for sine, adding two things together. So z1, z2 is equal to r1, r2 multiplied together, cis theta 1 plus theta 2. So this says if we're multiplying together two polar complex numbers, take the two moduluses, multiply them together, and take the two arguments and add them together. And let's use that right now. So here we have two rectangular complex numbers, and I want to find their product. And you say, but you know what? I can do this. I can just multiply them together by foiling. It's not that bad. Well, you're right. But remember, we're building to something here. Multiplying in polar form is going to lead us to exponents in polar form, and that, ladies and gentlemen, is awesome. So let's turn both of these into their polar form. So z1, where is it? What's in quadrant 2? It's over here. And we have negative 2 and 2. So z1 in polar form, the modulus is square root of 8, or 2 root 2. CIS 3 pi over 4. Z2, well, where's that one? Z2 is down here in quadrant 4. Its real part is 3 root 3, and its imaginary part is negative 3, giving us a modulus of 6, CIS, and the argument is negative pi over 6. We could have said 11 pi over 6, fine, doesn't matter, I don't care. I'm going with negative pi over 6, well, because it's a smaller number than 11 pi over 6. And now Z1 times Z2, here's where it gets slick. All we do is multiply the two moduluses. So 12 square root 2, cis, and then we add the two arguments together. 3 pi over 4 plus negative pi over 6. We need a common denominator, and we get 7 pi over 6 as our final answer. 7 pi over 12 as our final answer. So here's our product in polar form, but what if I want my answer in rectangular form? Oh man, what a pain. Well, it is a little bit of work, but we're going to realize something kind of cool at the end. I hope you like where we go. So this is 12 root 2 times cosine, and I'm going to rewrite 7 pi over 12 as the sum of two angles that I know unit circle values for. 7 pi over 12 is pi over 4 plus pi over 3. And you'll see why I'm doing this in a second. Plus I sine pi over 4 plus pi over 3. And we happen to have trigonometric identities to allow us to evaluate the sum of two angles. We know that cosine theta 1 plus theta 2 is equal to cosine of the first, we'll call this A and B, times cosine of the second minus sine of the first, sine of the second. So I've got 12 root 2 times cosine pi over 4, cosine pi over 3. Those are both things I know, minus sine pi over 4, sine pi over 3. And then we're going to do plus I times, and you might be going, ooh, we had an identity for sine also. We saw it back when we derived our product rule for multiplying polar form complex numbers. It was sine alpha, sine A plus B, was cosine of the first, sine of the second, plus sine of the first, cosine of the second. So we're going to have cosine pi over 4, sine pi over 3, plus sine pi over 4, cosine pi over 3. And we're going to substitute our numbers in now. So 12 root 2, unit circle time, here we go. Cosine pi over 4, root 2 over 2, cosine pi over 3, 1/2, minus root 2 over 2, sine pi over 3 is square root 3 over 2, plus I times okay, you're going, wow, that's crazy, that's ugly, I don't like it, it's garbage, who cares? Well, I care, so I'm going to keep going because I know something cool is about to happen. And what we end up with is root 2 minus root 6 all over 4 plus I times root 6 plus root 2 over 4. And you're probably going, who cares? Well, compare for a moment the rectangular form, which is this one, that's our Cartesian form, with our polar form. What we have just done is we have found an exact value for cosine 7 pi over 12. It's right there. And we found an exact value for sine 7 pi over 12 right there. And you know what? I think that's kind of cool. We took this non-unit circle angle. We didn't use any of those trig identities other than sum and difference identities. We didn't use the half angle or the double angle identities. And we were able to use our knowledge of complex numbers in polar form to find the exact trigonometric measures for 7 pi over 12. And we can do this with a lot of other angles also. Neat, cool. I hope you think so. On we go to division. So we're dividing these two complex numbers, z1 and z2 again. And I'm not going to go through all the nitty-gritty, dirty details of this, but the first step would be, well, when we're dividing complex numbers, we multiply by the conjugate of the thing we're dividing by. And doing our expansion, we get R1 over R2 times, we end up getting 1 in the denominator, and in the numerator we end up seeing the sum and difference, or the difference identities for cosine and sine, and we get cosine theta 1 minus theta 2 plus I sine theta 1 minus theta 2. So z1 divided by z2 is the quotient of the two moduluses cis difference of the two angles. And that's where I'll leave you. We can do a lot of the same sorts of things with division like we did multiplication, but this is where I'm going to stop. It's getting long. A lot of cool stuff happened here. I'm going to leave you to party with your practice.